Have you ever wondered how we go about wrapping a standard linear wave around a circle to create a polar graph like this? Mathematically mapping a signal this way is what allows algorithms to eventually decompose audio and radio waves into their individual parts. To build this, we have to establish our baseline variables. The time period, capital T, is the duration to complete one single cycle. Next, standard frequency, lowercase f, is the inverse of the time period, 1 over t, representing cycles per second. Finally, since one cycle equals 2 pi radians, we multiply frequency by 2 pi to find the angular frequency, omega. We can see this relationship in action with a quick check. If a wave's period is exactly pi seconds, its frequency is 1 over pi, making its angular frequency a clean 2 radians per second. Now let's build the coordinate system that spins our wave. We start with the baseline for any circular motion. A point traveling along a unit circle is defined by cosine theta for the x-axis and sine theta for the y-axis. We apply this rotational mapping equation to spin our wave. The function f of t dictates the signal's amplitude. The omega t inside the cosine and sine acts as the spinning engine, while the negative sign ensures clockwise rotation into a two-dimensional space. You must track two frequencies simultaneously: the signal frequency, capital omega, representing our 5 Hz data, and the rotational frequency, lowercase omega, our arbitrary spinning speed. Substituting these into the mapping equation gives us this specific coordinate pair. Let's test a complex signal with two frequencies, 5 and 7, spun by a rotor set to 4.27. This complex spirograph is the visual result of these multiple independent frequencies interacting on a mathematically mismatched rotor. When our rotation frequency, lowercase omega, does not match the hidden signal frequency, the graph forms a symmetric shape, perfectly centered over the origin. Because of this symmetry, the shape's center of mass remains exactly at 0. Here, our rotation frequency perfectly matches the signal frequency. The entire graph shifts, displacing the center of mass away from the origin. Tracking this center of mass shift is how the Fourier transform isolates the frequency of a hidden signal. Here is a mathematical cheat sheet for these concepts. Take a screenshot to keep it handy. Next time, we translate this shift into the language of integral calculus.